In this video, we're going to look at a key process for our area calculations, which is estimating the area. Maybe not getting exact values, but having at least a systematic approach to getting a close estimate for the area. Take, for example, this graph here. If we want to find the area beneath this graph of this function on the interval from x equals 1 to x equals 4, that would be this interval here, then what we're talking about is the area shaded in this region here. That would be the region A. This area is definitely not something that we can look at and get the exact area out of it. So what do we do instead? Well, what we can do is start off by making rough estimates and then hopefully find a strategy for improving them. Let's draw a rectangle that completely contains the area. So imagine we're looking on this interval here. We want the area underneath this graph. Well, this graph gets bigger and bigger and bigger. So if I made a rectangle that was this tall and had that as its shape, let's round it off there, that rectangle would be larger than the area A, which is the area underneath the graph. And we can also get a value for this. So the area under A, or area defined by A, we don't know, but we can certainly find the area of this rectangle, which is 3 on the base by the height, which is about 4.5. And so that would be 13.5 square units. So whatever the area A is, it's less than 13.5. Well, correspondingly, we can also look on the same interval and say, well, the function never goes below 1. So if I could build a rectangle like this, I would have the A area being larger than the green rectangle area. And that green rectangle area is a 3 wide by 1 high, or 3 square units. Is that helpful? Depends on your perspective, but we certainly know a range under which the A area can fit. It has to be less than 13.5, and it has to be more than 3. I will admit that's pretty crude. This is like 3 times difference. It leaves a lot of room in the middle to fit A, but hopefully this gives us a strategy for finding an estimate and then maybe getting better estimates. The key to that strategy is using smaller rectangles. Let's take that same interval again, but this time we're going to break it up into 3 smaller intervals. So from 1 to 2, from 2 to 3, and then 3 to 4. Let's estimate this with the function at the left edge of each interval. So let's take a look at this region here and imagine for a second trying to capture the area underneath the graph. Recognizing that's too challenging because we don't know how to find areas under curved lines yet. So what we do is we just do an approximation and say, well, it's going to be at least this much. Now that does not look like an improvement on what we did last time. We had a square or a rectangle of height 1 last time, but see what happens when we do the same thing on the next interval. Let's take the left endpoint here and build a rectangle that high, and then a rectangle again on the next interval that's as high as the graph is. And you see those 3 rectangles together are much closer to the area underneath the graph. We're missing a little bit here, a little bit here, a little bit here, but they're much closer in area to the area under the graph because we were able to subdivide our problem and focus in on certain subintervals rather than trying to do the whole estimate at once. And once again, we know that the area A is hard to find right now, but we can say it's approximately, we won't say less or greater than at this point, we'll say it's approximately the area of these 3 rectangles. And each one of those can be computed with a height times width calculation. So we'll write that down as 3 separate terms. We could put subscripts if we wanted. First rectangle, second rectangle, and third rectangle. And then we can put in the values. In this first rectangle, the height is 1, and the width is 1 as well. On the second rectangle, the height is 3, and the width is 1. In the third rectangle, the height is 4, and the width is 1. Keep it consistent here. So that gives us 1 plus 3 plus 4, or 8 square units. And visually, that appears that it'll be a much closer value to the exact area compared to, going back a slide, the overestimate we had before in blue or the massive underestimate we had in green. Now we're honing in on the real exact area under this curve. It's still a little crude, but it's a big improvement over our first estimates. Hopefully you see the theme at this point, or the direction we're heading. Hey, what if we increase the resolution, if you think of graphics, by using smaller and smaller rectangles? We could see already that if we used half the intervals, we would be able to fill in some of the space that we're missing underneath this graph and get an even better estimate. So that strategy is how we're going to move from these very crude estimates to more and more accurate estimates, and eventually to exact areas under curves.